Hello, we are from EIE 3360 and we are group 34 and this is our group presentation. I'm Long Chen Q. We are building an autonomous robot car for some football scoring challenges. And we used the YOLO version 5 to work on the object detections in real time. And this implementations of AI has basically two features. One is database sourcing. So we improved our dataset for the detections by adding more new pictures for the dataset for around 500 pictures. And for the detection reaction, we keep adjusting our Python codes to make the car working out a consistent detection and scoring patterns. And for the achievements, so for the first demo, we successfully scored all 3 challenges by mostly using the target cards to detect the goals. And then for the final demo, we scored all 4 challenges without using the target cards, but we used by targeting the goal, used by implementing a long-range shooting methods. For the detection accuracy, by the end of our model training, it was around 85% of the precisions in some real-time detections. However, by the time till the demo, it was around 60% of the precisions. For the key features and the innovations, so first of all, we used the AI to assist our annotations of all 500 pictures. As the RoboFold supports with an AI assist tools, we're not totally letting AI to help us annotate all of them, but they help us to annotate those that we have already annotated, so that we can reduce the time to repeat all the things that we annotated, and we spend most of the time in checking whether it has annotated some wrong pictures or not. For the first demo, we did not use all the detection zones, but we only used 2 lines for 3 detection zones, left, middle, and right, so to work out a more effective real-time performance for the first demo. While for the second demo, it will be more complicated with many of the lines. It will be elaborated more in the methodology part. And for the speed control scoring, our robot used the speed adjustment to make the scoring methods, so that it can use the turning to help us score a long-range shooting. As our project's background is about object detections, and it can be used in many fields. And this time, we use YOLO version 5 for our AI-driven robotics, and NVIDIA Jetson Nano for the real-time graphic processing through the webcams, and the STM32 microcontrollers works at the car base for us to use for the movements of the car. There are some of the challenges that we faced through the sourcing part of the datasets, such as the datasets having some of the classes suddenly disappeared. We are facing the processing latency through the tight VNC that we used to monitor our car's webcam. And also the webcam may have some color deviations that may affect to our object detections. And the reason why we implemented real-time processing is that it's very important for us to make automations for the computers to do immediately making some decisions. And also, our cars are placed in different positions of the starting point, and also the boards are always different. These dynamical environments will always help us through AI to deal with different positionings of our targeting objects. And our project objectives is to develop a real-time object detections with multiple objects, such as the balls and also the goals that we have just mentioned. And we also use Python codes to help us do the navigations through the autonomous system. And we enhance our RoboGap to help us to enhance the shooting procedure, to enhance the shooting scoring rate.
My name is Chen Kafeng, and now I'm going to talk about the methodology of our project. First, I will talk about the football detection logic. And in our code, we will divide our camera frame into 3 regions by using 2 vertical lines. And we will define the frame into left, middle, right region. When the bounding balls of the detected football is on the left, the robot turns left. And if the bounding balls of the football is on the right region, the robot turns right. Until the bounding balls of the football is lines in between in the middle center region of the camera frame, the robot start moving towards the football. And when the robot is moving towards the ball, the bounding ball size draw will become larger and larger. And when the size become larger than the threshold, the robot stop moving towards the ball, because this means that the ball is already very close, or the robot has already obtained the ball. And then it will activate a mission flag. And according to different challenges, we will enter different logic loops. And here is the flow chart of the code logic. When the robot car detects the football color, for example, it detects the red football, it will enter the red football loop, which means it is doing the first challenge. And after the robot had obtained the red football, it will start finding the white gate. And if the robot at the beginning have start to detect the orange football, then it will start to find the blue gate. This method can avoid the robot to detect other not related gate. For example, if the robot have detected the orange football, after he get the football, it will only detect the blue gate but not the white gate. And for the red, green, blue football, it will only detect the white gate but not the blue gate. Set this method to ensure that the corresponding football is only responsible for the corresponding gates for different challenges. And for the gate detection, we have to face a very big problem, which is that after we have trained a lot of different YOLO models to increase our accuracy, we discovered that only the orange gate have give us a relatively good performance, but the blue and white gate is not as good as our expectation. It flows blue gate, white gate during the robot car is moving. So we cannot directly use the blue gate and the white gate to tell the robot to detect them. So we have implemented a new logic to handle this problem. And for our gate detection, as we only have a good performance on orange gate, we only reference the orange gate for all the gate detection. The logic is similar in this picture. When the robot moving to the point and found the ball, it will start to find the gate. And it will first detect the orange gate. When the robot see the orange gate, depends on the challenges. For example, we need to go to the white gate. The robot will turn right to find the white gate after the robot see the orange gate. And we also have the boundaries lines to guide the robot to turn to a specific angles to find the gate. When the robot see the orange gate, it will turn right to find the white gate. When the bounding box of the orange gate has passed these boundaries lines, the robot stop turning, because when the orange gate already passed these vertical lines, which means that the robot is already facing the white gate. Or on the last challenges, we need to find the blue gate. The robot turned left when it saw the orange gate. And when the orange gate have passed the left hand side these vertical lines, which means the robot has already turned and facing the blue gate. We use this reverse logic to for the robot to find the white gate and the blue gate. By using this logic, we can avoid directly using the blue gate and the white gate, which we've failed to detect. So we implement this gate detection to find the white gate and the blue gate. And because of this gate detection, we have implement a shooting logic for the robot. Instead of pushing the football, we shoot the ball to the gate. For example, in this picture, this is doing the blue football task. When the robots start seeing the blue ball, it will find this using the method I have told before. And then at this point, we stop near the blue football, as it has already detected it and found it. And then it will use the gate detection logic to find the location, or you may say the direction of the white gate. And then it will start moving towards the gate and shoot the ball in a fixed position and predefined weight. This can reduce the time for the robot to find the gate. And in the previous method of our code, the robots find the ball, use time to find the gate, and then slowly approach to the gate and push the ball to the gate. So to minimize the detection errors, we fix the starting point of the shooting spot in the green area, as you can see in the picture. And every time when the robot goes near the balls, whether it have pushed up the ball a little bit or didn't push the ball, the robot will stay in this green area. And then it will find the location of the gate. And then it will start the predefined road to go towards the gate and shoot the ball at this fixed point. And it can increase our mission reliability as it is more reliable. And now I will talk about the implementation of our project. And we have labeled 14 classes totally in our dataset: the 3 gates, the 2 yellow cards, and the 4 feather football, and other 5 types of invalid balls. And the invalid balls is not used in our final demo, because we have found out that the invalid ball is not necessary when we have a very good accuracy on our feather football. The robot will not wrongly detect the invalid ball as the required football. So that is not used in the last demo. And totally we have 508 annotated image in our RoboFlow dataset, and we have found out that the red football and the blue football is underperformance. And we have discovered that the red football and the orange football seems like it's very similar to the model. It cannot have a good separate well between the red ball and the orange ball. So we have added more image only for red ball and orange ball to the dataset to train the model again. So after all, the robot head can distinguish the red ball and the orange ball about 0.8 confidence. And for the blue ball, we have noticed that maybe because of the blue ball is relatively more dark in color and similar to the gate, so it will have a bad performance in our previous model. So we also add more pictures and image of blue balls to the dataset to train the model again. And initially, we used 200 epochs for training the models, but we found that using 200 epochs is still not have a very good performance for completing our task. So we finally increased to 400 epochs for the adjustment. And finally, the performance is good, but just like what we have faced before, the football confidence have improved a lot. And to overcome the different confidence and different accuracy of our object, we use different confidence levels in our coding. And for the general confidence setting, we use 0.6 for the footballs. For the green, red, orange footballs and the other gates, the orange gates, it can provide a good performance in detecting the colored footballs. But for the blue football, although we have trained the model again and adding more image to improve the accuracy of the football, we found that in the final performance, the blue football still is in a comparatively bad performance. So we separately use the 0.4 as the confidence level of blue football. We have studied the challenges. As in the blue football challenges, it only requires us to recognize the blue football. And so using 0.4 confidence is okay for us to finish the task. So we separately use 0.4 for blue football and 0.6 for the other general settings.
And I'm here to talk about more of the implementations of some mixture of software and hardwares. So one of the software that we also use in this project is Tinkercad. It helps us to build the modularized grippers. And these are some of the screen captures about how we designed it. And for the left side, it is how we used it to measure the size of the modularized part. And the middle one is how the entire part is designed by each component. And the right side would be the working out of it. And also we found that our gripper can actually have different formats. So it's capable of different formats to change whether we are going to shooting through taking the ball directly to the goal or through the gaps that we score by moving, turning left or right. Then this is some of the captures to talk about some little adjustments that we can do for our grippers, including one of them are the screws, so that it can do some adjustments dynamically. And these are the captures about our evolutions. For top left corner, it will be the first generation of our grip. It was okay, can be used, but we implemented more with the gripper modulized, so that even though for the right side you may see that one of the grippers are broken, we can immediately change it through some of the repairing. And this can reduce the time for us to rebuild the entire gripper again and again.
Hello, I'm Something Hong and I will present the results and evaluation parts first. Okay, and this is the image of our model result. For our model indifference football detection, when it was doing the detection on the green football, it always provides the correct detection on it and the confidence level can keep higher than 0.85. For the red football detection, it can still keep high confidence too, but it would easily detect a red football as an orange football. And for the orange football, the situation is the same. The reason that we guess is because these two balls are too similar. And for the blue football detection, the accuracy is lower than another football. As the model training results, we can find that the blue football MAP score is the lowest in all detection. And for our model indifferent gate detection, we found that the orange gate has the highest accuracy in all gate detection. When the car was moving, it could still stably detect the orange gate. For the evaluation parts, we'll talk about for the model. The model can perform well in ball detection, but for the gate detection, the model can perform the most stable performance in orange gate detection. So that we will choose the orange. We will choose the orange gate detect to use on the main role control in the whole demo part. Okay, and then for the method, we have used shooting to instead push the ball to the gates. Because using this method is based on the speed and stability. For speed part, it can reduce the time of finding the gates and let the car move to the gates with pushing the ball. And for the stability, because shooting can reduce the chance of the touching between the football and the grab. We have observed that when the ball and the grab keep touching, the roots of the football moving will become unstable. So that we choose this method can reduce the touching chance between the football and the grab. Finally, we can keep and meet the objective efficiency by using this method.
Now, let's have some more discussions about the implementations of AI. Through the development of the data sets, we always found that through those 500 annotated images, some of the objects may not always be detected at the high rates of the confidence thresholds. And we found, especially for blue balls, as other balls are at the 0.6 precisions, only blue footballs are having 0.4. And this may show us some of the potential problems that blue balls may sometimes be detected like similar to some black balls or black objects. So that we always have to balance some of the false negatives and false positives through the exports of the trained datasets. And also, we found that it is very important to always look for hardware's enhancements. This time, we used the 3D printed grab for us to help us score through a long range of the shooting. So we found that the black base is actually mounted on the car, while the white one is used to do fine adjustments to make the scoring more successful. And this helped us to think about how our car can actually implement it in our daily challenges, such as autonomous delivery. Similarly, they are both carrying on some of the objects. This time, our car is developing to move the football, and developing the autonomous delivery helps to deliver some of the goods, products, or maybe some boxes. They both have the ability to do adaptable detections, and also through Python code, it can do some navigations and some movement logics. And also, it can be used to do assisting robots to help some of like elderlies to take care of their lives, and also for some of the surveillance systems to monitor like CCTVs, to monitor buildings, whether there are some of the many peoples are coming all around in the large buildings, and so more implementation parts. And let's talk about the society and the global impacts. Through this project, we found that AI is so useful for us to boost the productivity like the annotation parts and also the safety to ensure that our cars are always moving inside our area and able to stop but not crashing on the goals. And it is very affordable and is modular designed for some of the resources limited settings. And we also are able to use some open source tools like the YOLO version 5 and maybe some RoboFlow and apps, and also the software for 3D printings like Tinkercad. And for some of the ethical considerations, we found that the dataset imbalances are some risks to our algorithmic biases.
Okay, for the second part, I will talk about for the conclusion and the future development first. And the future development. And I will talk about the conclusion part first. Okay, for the conclusion part, here's the key finding. In this project, we learned to make selections of the dataset sourcing and experience in marking and adjusting all the labels and classes to fit our demonstration requirements. By implementing loops on detect object, our robot car managed to score by cases and discovered that changing the mounting method of the gripper can significantly increase the chance of catching the ball, and also affect the alignment of the football scoring path and the target goal. For the reflection, we found our team to be successful with the work distribution not only because we managed to separate our workload evenly, but also able to work in parallel. For example, we separate our team to deal with the dataset training failure problem and work on the scoring Python code and working for the scoring Python code. Or maybe two teammates working on new car logic adjustment and one work on the gripper for the grab upgrade. We found the importance of work distribution to maximize our productivity under a very limited time of work. We evenly swap our roles along the main workflow. Understand as all of us participate through the database sourcing and annotation, setting up the tight VNC and make program adjustments, and the observation of the gripper performance and mix modify of gripper. Contribute to our responsibility in everyone roles. We managed to maximize our productivity throughout numerous of troubleshooting and enhancement, successfully delivered a work prototype that met its core objective, demonstrating the potential of AI-driven robotics. However, challenges like hardware latency and time constraint revealed areas for improvement. Future efforts should prioritize process efficiency and system scalability. Overall, the project offered valuable lesson in integrating AI with robotics, emphasize the role of iterative development and creative problem solving. Okay, for the future development part, we'll separate it to the software and the hardware development. First, I will talk about for the software development. For software, I will try with different deep learning models other than YOLO 3.5, such as SSD, and compare the performance for a more reliable object detection model. Then we'll find a better application or connection method to increase the fluency of webcam monitoring. TypeVS is a stable application for our portable PC is to connect the car, but it's always drop the FPS and the highest FPS of it, and we can only set it to 10 FPS, so that we'll find a better application in the future. For the finally, we'll use more professional 3D models apps to design our graph. For example, the Fusion 360 is support more features to help strengthen the broken part and it can make the graph be more durable. Then I'll talk about for the hardware development. First, we're using a more secure connection between the computing module and the robot car, and we will lower the center of gravity to make our scoring is more stable. Then I would like to upgrade the motor components to help stabilize the movement of the robot car. And based on the modularized feature of our grab, further design can be implemented to equip the car with more different functionality, more than just scoring a goals. Okay, and this is the end of my part of the presentation. And thank you for your time.